Chapter number 6, Triangles. Unit 6.1, Introduction. Similarity of geometric figures is an important concept of Euclidean geometry. Transformation of a geometric figure proportionally to the other one of the same shape creates the similarity. As for example, a photograph, an object and its enlarged photograph is a simple illustration of the similarity of these two copies. For example, a map of India hanging on the wall is similar to the map given in the book. The concept of similarity of geometric figures is used in many applications. The heights and distances which cannot be found out by direct measurement are measured using the principle of similarity of figures. Note, in congruency, the shape and the size of one figure is the same as that of the other figure. In similarity, the shape of the figures do not change, but the size of the figures change proportionally. Unit 6.2, Similar Figures. Look at these figures. Are they exactly the same? No, their shapes are the same. Then in what way do they differ? Yes, they differ in sizes, though the shapes are exactly the same. You know such figures which have same shape but different sizes are called the similar figures. You have studied the elements of a triangle. Which of these elements will change the shape of the triangle? Yes, the angles will change the shape of the triangle. When we say two triangles have the same shape, that means the corresponding angles of these two triangles are of equal measure. In order to understand the concept of similarity, let's do one activity. Cut out a triangular figure from a piece of cardboard. Hold it between a point source of light and a screen. Observe the shadow cast by the figure on the screen. The shadow will have the same shape, but is larger in size. The shadow A', B', C' is similar to the original triangular cutout ABC. Look at these two circles. Their radii are the same. We know that these two circles are congruent to each other. What about these two equilateral triangles with the same side level? Yes, they are congruent to each other. Consider any two triangles with the angles of equal measure. Are these triangles congruent? No, they are not. Although their shape is same, sizes are not the same. Since these two triangles are equiangular triangles, their shapes are the same, and hence they are similar triangles. Thus, we can conclude that all the congruent figures are similar, but the similar figures may not be congruent. In general, any two polygons of the same number of sides are similar if 1. All the corresponding angles are equal, and 2. All the corresponding sides are in the same ratio or proportion. Let us consider an example. Consider two polygons, quadrilaterals PQRS and LMNO. Here, vertex P corresponds to vertex L, vertex Q corresponds to vertex M, vertex R corresponds to vertex N, and vertex S corresponds to vertex O. The one-to-one correspondence is shown symbolically like this. In these two quadrilaterals, the measure of angle P is equal to the measure of angle L, which is equal to 70 degrees. The measure of angle Q is equal to the measure of angle M, which is equal to 85 degrees. The measure of angle R is equal to the measure of angle N, which is equal to 90 degrees, and the measure of angle S is equal to the measure of angle O, which is equal to 115 degrees. Now, let us find the ratio of the lengths of the corresponding sides. SP upon OL is equal to 1.8 upon 3.6, which is equal to 1 upon 2. The ratio of QR and MN is 1.5 upon 3. Is 1 upon 2. The ratio of the remaining two pairs of sides, that is PQ upon LN and RS upon NO, is also 1 upon 2. That means SP upon O is equal to PQ upon LN is equal to QR upon NN is equal to RS upon NO, which is 1 upon 2. Hence, the quadrilateral PQRS is similar to the quadrilateral LMNO. Look at these figures. The first polygon is similar to the second polygon, and the second polygon is similar to the third polygon. By the property of transitivity, we can say that the first polygon is similar to the third polygon. Can a circle and a triangle be similar to each other? No. By observing them, we see that they are not of the same shape and hence are not similar to each other. Consider any square and rectangle. Are they similar? No. Why? Well, even though their corresponding angles are equal in measure, their sides may not be in the same ratio or proportion. Now, can you comment on the similarity of a parallelogram and a rectangle? A parallelogram and a rectangle cannot be similar to each other as their corresponding angles are not equal. Now, in this chapter, we are going to study only similar triangles. 6.3 Similarity of Triangles.
Definition of similar triangles. For a given correspondence between vertices of two triangles, if corresponding angles are congruent and measures of corresponding sides are in proportion, then the correspondence is called a similarity of the triangles. Example, for the correspondence between ABC and PQR of triangle ABC and triangle PQR, if angle A is congruent to angle B, angle B is congruent to angle Q, angle C is congruent to angle R, and AB upon PQ is equal to BC upon QR is equal to CA upon RP, then the correspondence between ABC and PQR is called the similarity, and triangle ABC and triangle PQR are called similar triangles. In symbol, it is written as shown. Note that for a given correspondence between the vertices of two triangles, if the measures of the corresponding angles and lengths of corresponding sides are in proportion, then the given correspondence is a similarity. Example, the correspondence ABC and PQR of triangle ABC and triangle PQR is a similarity. If measure angle A is equal to 70 degrees and measure angle C is equal to 50 degrees, then find the measures of angles of triangle PQR. The solution is as follows. Here the correspondence between ABC and PQR is a similarity. Therefore, angle A is congruent to angle B. Angle B is congruent to angle Q. Angle C is congruent to angle R. Therefore, measure angle A is equal to measure angle P is equal to 70 degrees. Measure angle C is equal to measure angle R is equal to 50 degrees. Now, measure angle P plus measure angle Q plus measure angle R is equal to 180 degrees, because the sum of the measures of the angles of a triangle is 180 degrees. Therefore, 70 degrees plus measure angle Q plus 50 degrees is equal to 180 degrees. Therefore, measure angle Q plus 120 degrees is equal to 180 degrees. Therefore, measure angle Q is equal to 60 degrees. Thus, measure angle P is equal to 70 degrees, measure angle Q is equal to 60 degrees, and measure angle R is equal to 50 degrees. Triangle ABC is similar to triangle PQR. AB is to BQ is equal to 4:5 and AC is equal to 6. Then find PR. If QR is equal to 15, then find BC. Solution. Here, triangle ABC is similar to triangle PQR. Therefore, AB upon PQ is equal to BC upon QR is equal to AC upon PR is equal to 4 upon 5. Since AB is to PQ is equal to 4 is to 5. Therefore, AB upon PQ is equal to BC upon 15 is equal to 6 upon PR is equal to 4 upon 5. Since AC is equal to 6 and QR is equal to 15. Therefore, BC upon 15 is equal to 4 upon 5. Therefore, BC is equal to 4 upon 5 into 15 upon 1. Therefore, BC is equal to 12. Now, 6 upon PR is equal to 4 upon 5. Therefore, PR is equal to 6 into 5 upon 4. Therefore, PR is equal to 15 upon 2, which is equal to 7.5. Let's solve another example. For triangle PQR and triangle DEF, the correspondence between PQR and EDF is a similarity. If PQ plus QR is equal to 15, DE plus DF is equal to 10, and PR is equal to 6, then find EF. The solution is as follows. There is a correspondence between PQR and EDF. Therefore, PQ upon ED is equal to QR upon DF is equal to PR upon EF. By the theorem of equal ratios, PQ plus QR upon ED plus DF is equal to PR upon EF. Therefore, 15 upon 10 is equal to 6 upon EF, since ED is equal to DE. Therefore, EF is equal to 6 into 10 upon 15. Therefore, EF is equal to 60 upon 15 is equal to 4. Therefore, EF is equal to 4. Let's solve another example. The correspondence between ABC and DEF of triangle ABC and triangle DEF is a similarity. If 3AB is equal to 2BC is equal to 4AC, AC is equal to 3 and DE is equal to 5, then find EF and DF. The solution is as follows. Now, AC is equal to 3. Therefore, 3AB is equal to 2BC is equal to 4AC is equal to 4 into 3, which is equal to 12. Therefore, AB is equal to 4 and BC is equal to 6. The correspondence between ABC and DEF is a similarity. Therefore, AB upon DE is equal to BC upon EF is equal to CA upon DF. Therefore, 4 upon 5 is equal to 6 upon EF is equal to 3 upon DF. Therefore, EF is equal to 6 into 5 upon 4, which is equal to 15 upon 2, which is equal to 7.5. Therefore, EF is equal to 7.5. 3 upon DF is equal to 4 upon 5. Therefore, DF is equal to 3 into 5 upon 4, which is equal to 15 upon 4, which is equal to 3.75. Therefore, DF is equal to 3.75. Remember that if corresponding angles of two triangles are equal, then they are called equiangular triangles. A famous Greek mathematician Thales gave the relationship between the two equiangular triangles. That is, the ratio of any two corresponding sides in two equiangular triangles is always the same. Now, let us study the basic proportionality theorem, also called as the Thales theorem.
We will read the statement of basic proportionality theorem. The theorem states, if a line parallel to a side of a triangle intersects other sides in two distinct points, then the line divides those sides in proportion. So, it is given that in triangle PQR, line L is parallel to side QR. Line L intersects side PQ and side PR in points N and N respectively, such that point N lies between points P and Q, and point N lies between points P and R. We have to prove that Pn upon Qn is equal to Pn upon Rn. That is, line L divides side PQ and side PR in proportion. Here, we will do a construction. Join segment Qn and segment Rn. Now, we will start with the proof. Consider triangle PMN and triangle QMN, where point N lies between points P and Q. These two triangles have equal height. Therefore, area of triangle PMN upon the area of triangle QMN is equal to Pn upon Qn. In triangle PMN and triangle RMN, where point N lies between points P and R, the height of both these triangles is same. Hence, the area of triangle PMN upon the area of triangle RMN is equal to Pn upon Rn. In the figure, we can see that the triangle QMN and triangle RMN have a common base M and are of the same height. Therefore, their areas are equal. That is, the area of triangle QMN is equal to the area of triangle RMN. Thus, we can say triangle PMN by the QMN in F triangle. Pm area of is equal to upon Qn, Pn upon Rn. Hence, the theorem is proved.